Hello everyone. So today we're going to be talking about pipelines and feature unions. And so these are going to be really useful tools for us. They're going to allow us to make what we might call better and safer models, models that are going to allow us to basically combine multiple models in a really nice, clean way. And so we're going to get into these feature unions and pipelines in just a second. But first, we of course need to start with some data. So let's read in some data. We're going to use pandas to do this. So we're just going to read in some data here. So this is going to be data that we're actually going to see again later, but it's going to be from the World Factbook. And we can look at it. Notice when we try to read it in, it looks a little bit weird. So if you remember, I think we've actually seen this before. We of course can pass in some arguments here to make it look a little bit better. So that's more like it. And so we see that this World Factbook data is a database with a bunch of different countries. It has a bunch of different features. So this is a pretty realistic data set that we might start with. In fact, it's actually a pretty nice, clean data set, so it's something that we might want to do. So what we're going to do here is we're going to model this data, but we're going to model it in, at first, a way that, as we'll see, is not particularly clean, and this will motivate how we're going to model some other parts of the data, and we're going to figure out how to do it in a cleaner and more efficient way that's also going to be a bit better for when we want to deploy such a model into production. So let's get started. Let's figure out what we actually want to model here. So what we're going to want to model here is what we'll call the target, and so this is actually going to be the GDP per capita. So this is the gross domestic product per capita, so per person. So this is going to be our target. And now if we want to get a sense of really what's going on, what features are important, we can actually look at the correlations. So we can do take a correlation between all of the different columns, and we can actually look at this only with respect to our target. And so this is going to give us some correlations. So here you see that something like the area of the country is not that heavily correlated with the per capita GDP. On the other hand, something like the exports is certainly, looks like it's very well correlated. So we see that these different features have different levels of correlation. One thing that we can do is it's just a pandas series, so we can look from some threshold. If we say the threshold is 0.25, we see here there's a bunch of nice features here that are going to contribute to this model. So what model are we going to use? We'll have to, of course, explore a few different ones, but one thing that we're probably going to want to do first is just look at these features. Let's just look at how they're behaving. Let's look at their scales, their distributions. So what we're going to do is this index here, this is going to be our features to start. So let's just save this as our features. Let's just make this a list. And so we can print out our features here. So this is the index of our features. So this is our data frame of features, right? We probably don't want this GDP per capita in there. So let's say I for I in features, if I is not equal to target. So this is our feature matrix here. Of course, I have to actually make them, right? So this is our feature matrix. So we'll call this columns. And then our feature matrix is just calls. And let's actually clean this up just a little bit by something like this. I for I in this, if I not equal to target. This is just a little bit cleaner. We don't want to reassign the name. So we can take away all that line of code and just do it in one line of code. and we of course have to remember that extra bracket there. So these are our features here, so we can pull them out here. So one thing that we might want to do, of course, is there's a few things we want to look at this from this features. So one of them is going to be the distributions of these, right? So we may have varying distributions. The other thing that we might want to do is actually fill in these missing values, right? So notice that some of these values are definitely missing. So for example, for this first row, we actually have no columns, no values, and that's actually true for a few of them, but for most of these we have the majority of the values here. But we are going to want to have to do something with this NaN. It's not going to be necessarily useful to just have them in there. So we're going to have to do some transformation to actually fix the NaN. So let's keep track of a list of the things that we might want to do. So let's just look at the head here. So our list. So this is going to be a list of things we want to do. So one, we need to fix NaNs. This we can do using an imputer. So we're just going to keep track of that. So now, what we also might want to do is actually look at the distributions of these things. So let's look at the distributions. So we can loop through these features, right? So we can say for feature in features, we can print out, we can get the feature, right? And we can actually make a histogram. So let's look at these on a histogram. Let's make an alpha like 0.5. And we also have to import matplotlib, so let's do that up here. So now we've imported matplotlib. Let's now actually run this plot. And it looks like we are getting some sort of error here. So what is our error here? It looks like something is the minimum value is actually less than the maximum value. So this is an interesting error. Do note that in this notebook, I'm going to be debugging my code as I go along. This is to try to kind of teach you about how exactly this works. So if we look at this, right, let's just print out df of feature.values. We see that this is looking a little bit odd. There's a lot of NaNs. There's a lot of other values, right? So I think what's going on here is that it's not able to deal with the NaNs. So what we can do is we can use the PD not null. So let's look at what that does. So we can index into this with the df feature of PD not null feature. Right, so now, let's see. So we don't want to do this, we want to do df featured, something like that. And this is going to give us just some values here, right? So if this is the data frame that we're using, so this is what we might call clean, now we can actually perform the histogram of clean, and we see that it works. And so again, the problem here was that we were trying to make a histogram. We didn't have all not null values, so this is going to be a bit of a problem. So not an issue. We were able to clean it up. We were able to use this PD not null function to get only the not null values. And what do we see? Well, one thing we see is that these have a tremendously different scale, right? So if we look at a lot of these features, for example, some of these features are on kind of the thousands or hundreds level. Others are in a dollar figure, so they're in the like trillions of dollars or billions of dollars. And some of these other features, so these features are all on very different scales, right? So another thing that we're probably going to want to do is scale this data. So we're going to have to scale the data. We can use something like a standard scaler. So that's great. Then the last thing we might want to do is fit the data, right? And let's say we want to use a linear model to do this. That's probably a good first attempt. Maybe we'll use other models too. So let's get started, right? So we've taken a look at this data. We can see that there's some wildness going on here, right? We see a lot of things are kind of between 0 and 1, 0 and 1 each of the 12. So let's set the x-lim from 0 to say something like that. We see we just get this absolute mess, but there's some features that are still just there. So clearly this is going to be a bit of an issue. It's something we need to fix. We'll do that by scaling the data. So let's first fix this NaN, right? If we're going to scale the data, we probably want to deal with the NaN. So one tool that's going to help us here is what's called an imputer. So here is the documentation for an imputer, and what it does is it completes missing values. So it's going to basically take a specific missing values type flag, and it's going to do something with them. So it's either going to replace them with something like the mean along the axis, or the median along the axis, or the most frequent. So there's different strategies for how you replace them. And then there's also an axis. So usually you're going to want to impute along columns. So you're going to look at the rest of the features. So what the idea here is that when we see a missing value, we don't want to just leave the NaN, and we don't necessarily want to get rid of the row. So a strategy we might take is to actually fill that value with the mean or the median or something else of all of the other values. So this is going to be our preprocessor. So we can import this. So it's from scikit-learn.preprocessing. We can import an imputer. So we can make an imputer. Let's just take the standard. We should be able to do a fit transform on our data, right? So here we have our data, which is df of features. So here what we're going to do is we're going to call this x. So we're going to work with these as numpy arrays. So we'll say x is df features dot values, and we'll say that y is df of target dot values. So this is just so we get kind of reasonable things. So we see these are those values there. So, okay, so we have this imputer. The other thing we're going to want to do is we're going to take out, before we do this, so right when I did that, I notice now that there's some values of our target that are NaN. So certainly we don't want to be dealing with that. If countries don't have a GDP, we probably don't want to be looking at them. So again, we can use this not null function to compute this. So let's first compute a clean indice. So we can compute something like a clean index is PD not null of, let's say, df of target. Right, so this is going to give us a clean index, or a Boolean index, if you will. So you can see the first one is not null. So now we can look at y of clean index, or df of target of clean index. Right, so this is going to give us, or let's actually look at df clean index. Right, so this is going to give us only those values which are not null in the GDP. So you see that even though some of these other columns might still be NaN, so we'll still need to fix those, this is going to give us at least all valid y values that we want to predict. So again, all we've done here is we've cleaned out the not null values in our y, because we don't want to look, it's not that useful to look at data when we don't have a label, right? If we don't have a label, then why are we doing unsupervised? Why are we doing supervised machine learning? So let's actually take these cleans. Let's take the clean indexes from these only, and now we get something that's a little bit cleaner. So you see that even though we have NaNs in our feature matrix, and we will have to fix those, our y label vector, if you will, is now clean. So we have values for all of those. Because these all have the same indexes, we're aligned on the y and the x. Great. So now we can use this imputer. We can fit transform our x. And notice if we print out something like x, and the imputer transform of x, notice that our original x had NaNs in it. Our imputed value didn't. So clearly this imputer is doing something. So now we have fixed the NaNs in our x. So we'll call this x imputed. So this has fixed our NaNs. So now we can make maybe a better histogram. We don't need to worry about these not nulls. So now what we're going to do is we can loop through our feature matrix. So for I in range x imputed of 0, we can plot .hist x imputed all rows that column. This has to be a length. And you see we get a similar histogram, but we don't need to check for NaNs because our imputed data has all of that cleaned up. So this is fantastic, but we notice there's still this issue of scaling. So when we want to do scaling, as we learned last time, we can actually produce let's see, we can import a standard scalar. So now we can instantiate a standard scalar, and we can call that fit transform. So we'll call x scale equals scalar dot fit transform of x imputed. So that's great. So we've now done a standard scaling, and now we can change this from imputed to look at the x scale, and let's see what we get. Much better. So it's not perfect. We still have some weird data. We see there's still these outliers, but the majority of our data is now centered at 0, has unit variance. So this looks a lot better. So we can probably fit a machine learning model to this. So let's look at what features we're actually using. So notice these are these features. So let's look at what's going on here. So we see that we have a few different types of features. We have kind of these electrical features. We have something like a natural gas feature. So we have, these are features, maybe I combine the oil and the natural gas and the electricity. These things are pretty well modeled. These are natural resources type things. We also have imports and exports, and we have things like internet hosts and internet users. And so you might imagine that we might want to do some further transformations on each one of these. So we could, if we want at this point, we could actually fit, let's say, everything to a single model, but maybe that's not what we want, right? Maybe we actually want a different model for each one. So let's make a first model here. So let's define or use a model. So let's say that we want to first make a model that's going to be our energy model. So this is going to model the energy, and here we're going to use a linear regression. So I will import a linear regression. And then I can fit the energy model. I can fit, definitely it's going to take y. And now I'm going to need to select out the features that I care about. Well, I don't actually know which features I care about here, right? This is going to just fit all of them. Let's say that I only want certain features. Well, if I only want certain features, what I'm going to have to do is write some sort of transformer. So here I can write my feature select transformer, and this is going to inherit from base estimator and also transformer mixin. But of course I need to import those. So I can say from scikit-learn.base import base estimator and transformer mixin. So here now we can do base estimator and also transformer mixin. So this is going to be a function which is going to take the columns that I want. So maybe I'll take self and columns. And in this case, what I'm going to do is I'm going to keep track of these features. I'm going to pull out the indices that I care about. So I'll just say self.columns equal to columns, and then self.indices is going to be I for I in, let's say, range of features, if features, let's do this a little bit differently. So it's the index for I feature in enumerate features, if feature in self.columns. This is going to give me the index of the features that I want. And then then we'll just check. So if the length of this is, let's say, less than 1, we'll raise a value error of, need to select at least one feature. So that's my init method. So then in my fit method, well, I don't really need anything here, right? I'm just selecting out features. So I have to have this same syntax here, but here, since I'm choosing the column in the hyperparameter input, and the fitting method doesn't need to do anything, so I can just define a transform method, right? And what my transform method is going to do is it's going to select out these indices, right? So what I can do is for each row in X, so I can return I can return Ella for Ella in enumerate row if I in self.indices for row in X. So I maybe could have done it a little bit simpler with some slicing in NumPy, but this is a very, I think, a little bit more intuitive way of doing this. So what I'm doing is I have the valid indices. I'm looking at basically the element if it is that particular indice. So let's make sure that this works. So one thing that we might notice is that det external and electricity consumption are the first two elements. So let's make some test data. So let's just say I have 1, 2, 3, 4, 5, 6, and then 7, 8, 9. So now if I create this transformer, so we'll call this FT, is going to be a feature select transformer of det external and electricity. Right now I can call ft.fitTransform on data. And what we see is we get 1, 2, 4, 5, and 7, 8. So it's really pulling out the first two columns. And let's say I change this to instead the third column, which is electricity production. This is going to be here. So we can see that hopefully this will pull out the first and third column, and we see that it does. So this feature select transformer is working. So now that we've tested that it's working, we can pull out for our energy model the data that we want. So we're going to do this from our original data. So we're going to be transforming X. So we'll call this maybe X energy. And our feature select transformer is going to take in, we'll pull everything here and then select what we want. So let's see what we want for energy. Electricity, yes. Exports, GDP, imports, no, 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 no. So these are all energy type things. That looks pretty good now. So again, what we're doing is we're selecting out the energy features and potentially some other features later, as we'll see. Let's just make this look kind of nice. Great, so we've now fit transformed this. So now we can use this X energy to fit this model. We're getting a little bit of an error. Let's look at what's going on. Here we don't want to fit X. We want to fit X scale. There we go. And that worked. And notice that we got a little bit of an error when we didn't use X scale because we used the original X, which doesn't have this nice clean data. So we did all that work to clean the data. Let's make sure that we used it. Okay, so we fit a model to our energy. We can see how well it's doing, right? Let's look at, let's make a prediction. So let's just make a plot of energy model dot predict X energy. We can also plot our Y value. And of course I have to call the right function there. So we see that this does maybe okay. It's not great. We can probably do a little bit better, right? In fact, it looks like for the most part it's maybe all right. But there's not really that much signal here, right? It looks like mostly this is just flat. Right, so our energy model dot predict. So if we just look at these two things, let's take their difference here. So let's just, to look at them together, we can take a zip of them. We can make a list of that, and we can look at sort of how these are comparing. We see it's not too good, right? There's this vast overestimate. So clearly this model is not that great. It's not particularly linear, right? That looks pretty bad. So remember, we can quantify this by looking at the residuals squared. So we can take the residuals squared and then sum them. I have to put a minus sign here, right? So we see that's pretty bad. Let's try something a little bit more flexible. So we can say dot ensemble. We'll just import a random forest. So let's use a random forest instead. It's a little bit more flexible. And actually, it looks like we've done maybe a little bit worse. So let's increase our n estimators to something like 20. We've done a little bit better. So that's okay. So this is not actually a great model. We're not going to care too much about this right now because the purpose of this notebook is not to make the best model that we can. The point of it is to learn about pipelines and feature unions. So if I wanted to kind of figure out how to make this better, I might do a little bit more feature engineering. I might also certain things like that. So we do have an energy model. Let's say if we make more estimators, if that gets a little bit better, not much. And now let me remember, was that better or worse than the linear regression? We'll use whatever one was better. So this was our old one. So it looks like the linear regression is actually doing much worse. So the random forest is doing much better, so we'll use that. So let's use the random forest. And let's use it with 20. Great. So now let's make a different model. So here we want a model that instead of looking at energy consumption is going to look at sort of everything else. So we have one model for energy consumption. Let's make a model for everything else. So we're going to take out the energy. We're obviously going to take out the feature itself. And let's take out all of these. This is going to be sort of all of our other stuff. And now to make this model, what we're probably going to want to do is have a new feature select transformer. So we'll call this FT2. We're going to want to fit transform this. So let's say x else equals ft2.fit transform. And this is going to be, again, x scale. So then let's make an else model. So we'll call this an else model. And this will be a linear regression. And then we're going to fit this to our x else and our y. And now we have our two models. So we have two different models. And now when we want to compare them, so let's say we want to make a prediction, we can take our feature matrix and we can make predictions with both these models and then take the average. But now let's go back. So let's say that I have some new data. So let's say I want to make predictions. And what I want to make predictions on, let's say my X predict. And here I'm just going to take, let's say, every fifth element from X. So here again, in general, this would be some new data or data that you set aside at the beginning. But let's just look at what I have to do to actually go through and make this prediction. So first of all, I have to run all of these different scalars at the end. So all of these different transformations have to run. Right. So the first thing I think I ran was the imputer. So I have to run the imputer. I have to call transform on X predict. And then I did something with the scalar. Right, those were two things. And then my energy, I had an energy, and that was this ft.transform. Then I also had this else mod. So this else data, this was ft2.transform. And this actually is an X predict. Let's say this is X. This is XP impute. I'm actually going to call this XP to make it a little bit easier to write. So this is XP, and this is XP. This is XP impute. This is again XP impute, and this is XP scale. And then I can fit transform XP scale here and XP scale here. And now I can finally make these two predictions. So here I can make the else model dot predict else data, and then I can also make the energy model dot predict energy data. And wow, so this is y else, and this is y energy. And now I have these two predictions. I have to run this first. And now I can take these two predictions, right? So I have a prediction YE and YEN. I can do a little bit of magic between them. So I can zip YE, YEN, right? So that's going to give me a tuple. And then I can take maybe the average value between them, right? So I can do something like, you know, A plus B divided by 2 for A, B, and this. And that's going to give me my full prediction. So this is actually somewhat problematic. It does work. We were able to build a model where we did a bunch of different transformations, where we had a bunch of different models for different parts of my feature matrix. But you can see how this is kind of messy, right? I mean, we have to remember that I have to do all of these things in order. I have to remember the order that I did them. I have to remember that this data is going to go to this model, and this data is going to go to this model. And it's all just kind of very complicated, right? There's a lot of things I have to keep track of, especially if I was going to take this particular model and move it onto another server or distribute it. This is going to get complicated. And this is a very simple model. As they get more and more complicated, this is just going to get more and more difficult to actually make usable. So luckily, scikit-learn comes to the rescue. So what we're going to do is learn how to simplify this. So what do we want? What we want is some sort of model that takes in our input data. This is this X matrix here, right? So we want to take in our X data, and we want to just have a model where we say model.fit XY. That should be it, right? That's what we want. So there's two ways we could think about doing this. So we could build a custom class that actually performs all of these operations in series, right? So we've seen that before. So if we notice, before when we made this linear regression class, right? We made a special linear regression class that selected out these features and then fit a linear regression to that, and we did that all in the class. So that's okay too, except that requires us writing a special class. It's a little bit brittle, it's hard to change things in and out. And so the solution to this is to use what's called a pipeline and also a feature union. So we can import from pipeline what's called a pipeline and a feature union. And so these things are awesome. So the first thing we're going to do is we're going to see how to recreate what we already have, and then we're going to talk about why it works. So we can make our model, and it's going to be a pipeline. And what a pipeline does is it takes a list of tuples of different models that I want to pass my data through. And a way I define these is with a string and then a model. So it doesn't have to be, the string doesn't actually matter in terms of its name. It just has to be unique in the model. And it's a way that we're going to be able to access these models. And so let's just look at this pipeline here. So if I call model.fit x and y, notice that what I get is a pipeline that has multiple steps. And so I can call fit transform actually. And what it will do is it will perform the imputation step or the impute step, and then it will perform the scale step automatically. So I don't need to define, I don't need to keep track of any intermediate data. I don't need to keep track of what happened when. So I can just impute it and then scale it. So a pipeline is when things happen sequentially. Now if I want to make a split, I can use a feature union. And so a feature union is something where both of the data or both things happen at the same time. So let's actually, we're going to call this union, but we don't necessarily want to make everything too complicated. So this has a similar sort of syntax, except now we have two things that happen on the same time, right? So we have one side, we have an energy model, right? And that's going to have some steps. And then we also have an else model, and that's going to also have some steps. So in our energy model, what we're doing is we're actually making a particular pipeline. So the energy model is going to take in a pipeline, and this pipeline is going to have a few steps. So the first step is basically a select step, and this is going to be this particular feature select transformer up here, right? So this is going to be the select step for the energy model. So we can define that up here. So let's say this is energy select, or we've actually already defined this, so why don't we just use it? So this is going to be ft, and then we're going to fit with a random forest, right? So this is going to be a random forest regressor with n estimators equal 20. And then our else model is also going to be a pipeline, and it's going to be a select with ft2, and then we're going to fit to a linear regression. And this is going to be a linear regression. And now there's one extra step that we have to do here. But before we go to that, so this is a nice union. Let's just look at the result of a pipeline if instead of a union here, I just fit a linear regression. So let's just get something that works, and then we'll implement the full model before. So this is going to do a linear regression on the full feature. Let's just comment this out for now. We will fix that later. So this model will allow us to perform a fit. So in this case, we of course need to put a comma there. So notice now we don't want to call fit transform because we have a model. We can just call fit. So this fit method is going to impute the data, scale the data, and then fit a linear model. So now when we want to make a prediction, we can just predict, let's say we have this xp, and we'll get out our predictions. So in this case, they're going to be basically perfect because we are taking in actually the feature that we care about. But the point here remains that we're doing this, we're taking in, we're applying the transformations, and then we're applying the fit effectively, easily. It just takes in our data. We don't need to keep recreating step by step what's happening. The data just gets passed through the pipeline. So remember, these first elements of the tuple don't actually do anything, they're just keys. It's the second element that takes an initialized model that's actually going to do the work. And so it's actually pretty easy to understand what's going on here. Let's just look at a pipeline here. And it's pretty easy when you look at the source code. So let's look at what happens in the fit method of a pipeline, and you'll see it's kind of easy. So all that happens is that you have this fit method here. So actually this underscore fit is what winds up getting called. So you start out with your feature matrix X, and then you go through each step. Now what each step does is it calls a fit transform. So every step is going to call fit transform, and then the final estimator is going to be fit. So everything is, there's fit transform for every one, and then at the end of the day, you get this final estimator that is fit. So that's all that's happening. Is here what's happening is first our data we call fit transform on the imputer. The result of that gets passed into the standard scalar. We call fit transform on that, and then we call fit on the linear regression. And so again, this is very powerful because it means we don't need to keep track of anything separate about our data, right? All of the information that we need is within this pipeline. So we don't need to, when we predict, we don't need to apply all these transformations again. The pipeline is just going to do that for us. Now, this is not just beneficial when you're sort of mocking things out or when you're working in the notebook, although it is very helpful. It is also extremely useful when you want to push a model to production, because on a production server, you have to remember the order in which everything goes. You have to make sure everything is uploaded in the right way. So this makes it very easy because it's just a single model. So yes, it's a model that contains other models, but it's just a single model. So what the pipeline does in some sense is it gives us a it gives us a nice sort of step after step process that we can pass our data through. So we pass our data through this pipe. What it doesn't give us is the ability to take different parts of our feature matrix and have them go through separate steps. And really, especially when you're dealing with unstructured data, when you're going to really want different pipelines for different parts of your data, having the ability to pass different parts of your data through different pipelines is going to be very useful, in fact, essential. And so this is very much what we did before, right? We had a different sort of pipeline for energy and a different pipeline for everything else. And so the way to do that is to make a feature union. So a feature union is different than a pipeline because each one of its tuples, which in this case are themselves pipelines, are run sort of simultaneously. At least you can think of it that way. So the original, whatever gets passed into the union, gets passed into both the energy model and the else model. And so you can see here what we're doing is we're selecting out in the first one, we're selecting out the elements we need for that. And here we're selecting out the elements we need for our linear model, for our else model. So we can put in this union here. So we've made the union here, we can pass it in here. So now we've made our model more like we did before. And I do need to remember to put commas when possible. So let's look at the error here. So there is one error here, and this is an expected error, which is that what needs to go into a feature union is actually a transformer. But these models themselves are not transformers. So what we're going to have to write is something called, we have to write a class that's something like, let's say a predict transform. And so this is going to be, again, a base estimator, and also a transformer. And what it's going to do is it's going to have a fit method, and it's also, which is going to return self as always, and also a transform method. Now, what this is going to take in is going to be a model. And so what it will do in the fit method is pretty simple. It'll just fit the model. And what it'll do in the transform method is it will return the predictions of the model. But it will return them not as a vector, it will return them as a feature matrix. So we can return something like self.predict, right? So we can make self.predict x, right? This is going to predict a bunch of rows, and we can make them, right? So what this is doing is it's taking a predicted row and it's turning it into a feature matrix. And this is necessary so that we can use these different transformers. So now we can wrap this class around our estimators here. And this basically implements a fit transform method, right? So now, when I fit this, I actually get something that makes sense. So I'm able to fit this. There's one more thing we have to do. So these are now transformers, right? So we've made transformers out of this random forest regressor. And so now we need to have another model which is going to combine these together. So often we might call this something like a blender model, and this will be a linear regression in this case. So now we can fit this. Let's look at what happened with the error. It looks like predict transform has no predict method. So we can define predict method. This will return self.predict x. We got a maximum recursion depth, so let's see what's going on. We need to do self.model.predict x. And the same thing here, right? We can't call predict. So actually, we didn't need this predict method. We just needed to call self.model.predict because we're predicting with the particular model, and now we get something that works. Again, this is not, we would need to do a lot of hyperparameter tuning and others to get this to work, but let's go on what we've done. So let's try to figure out what the purpose of this model is. So the big point here is that in a single model, we've now encapsulated all of the work we did before, all of the transformations, the sort of disparate models into one single pipeline, into one single model. And now when we want to fit or we want to make predictions with this model, it's only one step. So we take in our raw data into the model, and we also predict raw data. So we don't have to remember to keep running these different transformations on the model. And this is going to be very useful because notice how complicated this was before. We had to remember to do all of these different transformations. We had to remember the order in which to do them, which particular branches needed what particular model. And this is going to allow us to put that all together, right, in an easy way. And so the benefits of this are massive. It's going to make things simpler, it's going to make it easier to deploy into production, and it's also going to make it a little bit harder for us to make some mistakes. The other thing we've seen, we're going to talk later about the benefits of using ensemble models. And again, that will be when we're more concerned about making our models better. Here we're just really concerned about kind of the scikit-learn infrastructure of machine learning. But ensemble models are very powerful, and this is a nice way to do them. So let's just go over what this model is again. So remember that with a pipeline takes a list of tuples. Now each one of these tuples takes two arguments. The first argument is a string. this represents the model that we're using. The name of it doesn't actually matter, but you should use something that represents that step in the pipeline. It is a unique identifier for that particular step. The second argument to each tuple is the model itself, and it's not a class, it's actually an instance of a class. And so we can read out very easily what we're doing. So we have an imputer and a standard scalar, and what's going to happen in the pipeline is that every single tuple, except for possibly the last one, it's going to call fit transform. So it's going to call fit transform on this model, then fit transform on this model, then fit transform on this model, and then for the last model, it'll call fit. And so when you call model.fit, that's what happens. When you call predict, what it does is it calls transform with this one, transform with this one, transform with this one, and predict with this one. And at every step of the way, it passes the result from the previous step into the next step. And so that's what a pipeline does. Now what a feature union does is it also takes in a list of sort of tuples that are almost key value pairs. Here again, this first element of the tuple is just a particular name for that stage of the feature union. So we have two here, energy model and else model. But here the difference is that they don't happen sequentially. They actually happen, you can think of them as happening at the same time. They don't necessarily get computed in parallel, it depends on how you implement them, but they're computed independently. So whatever you pass into the feature union, which in this case is the result of this standard scalar, both that entire feature matrix goes into both this model, which in this case is a pipeline, and both this model, which is in this case another pipeline. And so these are really useful when you have different parts of your feature matrix that you want to treat in different ways. So in this case, we said we're going to model the energy in one way and everything else in another way. This is even more useful when different parts of your data really require different processing. So it's not just that maybe you have some data that's text and some data that's numbers, and you're going to need some way to combine those models together. Now there was one little note here that what comes out of a feature union, so unless it's the last stage of a model, it does have to be a transformer. And so we had to write this predict transformer, which takes in a model and makes it into a transformer by basically creating a feature matrix from its predict method after performing the fit. So that's what happens. It's just a little detail here that anything except for the last step potentially does need to have a fit transform method. So we had to wrap our random forest and our linear regressor in a predict transform so that they would have this fit transform method. Now what comes out of this union? What actually comes out of this union are the predictions from both of these models. So we get a prediction from our random forest regressor and also a prediction from our linear regressor. So what we then do is we make a linear regression from these predictions. And you can think of that as weighting the predictions from both of these models. So maybe one is a little better than others, so we're able to model a full model as basically some sort of weighted average, if you will, of these two models. So all of this, again, is very similar to what we did before, except we did it in, I would say, somewhat less code, and now we can call this fit and this predict in a much nicer way. So we don't need to worry about keeping track of every step that we're taking and making sure that every time we fit with a certain sequence of steps, we also predict with a certain sequence of steps. This is hard. This is not something that we want to have to do. So in practice, when you're actually building ML models, no matter what framework you choose to use, you will actually be using something like a pipeline often. This is really a useful feature. So the start of your pipeline is going to be to get the data from some sort of form. Maybe it's already in memories in this case, but often it's going to be reading it from a database or something like that. And at the end, you should have your fitted model. And so if you put everything into a pipeline, it's going to make your life a lot easier, much less prone to error. So we also looked at the code here, and I actually do encourage you to read through this part of the code base. It's done quite nicely, and you can really see what's going on. So again, when the fit method of a pipeline is called, the first thing it does is it calls this fit private method, and then it calls this final estimator fit. And so what this underscore fit method does is it takes each different transformer, right? So here, each different transformer, so this steps object contains all the different transformers in the pipeline. It does a little bit of fancy stuff, but at the end of the day, it just fit transforms that feature matrix. Now recently scikit-learn has added some functionality, so you see stuff here about caching. So what it does is if you're tuning a parameter in a pipeline and previous steps stay the same, it can actually cache the results of previous steps. So this can increase your speed at which you can train your hyperparameters. And this brings out one extra sort of goodie that you get for free with a pipeline. So we haven't talked much about hyperparameter tuning, but what that is tuning the exact values of things like this N estimators. Now, as you might imagine, if you have a big model and you have a lot of different, say, submodels in your pipeline with a lot of different hyperparameters, these things may actually be correlated with each other. So it may be that if you raise one hyperparameter on one model, you may need to lower a hyperparameter on another model, so on and so forth. And so having these things in a pipeline is going to make it a little bit easier to tune all of these hyperparameters together. And so later on, when we talk about hyperparameter tuning, we will talk about how to do this, and we'll talk about how to do it in the context of a pipeline. Great. So one last thing here, we can also use a pipeline just as a transformer. So let's make a transformer pipeline. Let's just take the start of this. So notice that if we just take the start of this, so this just scales, and it both scales and then it imputes. So we can actually call a fit transform on XP. So we can also make pipelines that are not just our full model, but maybe pipelines that are just a series of transformers that will transform our data. Now this can be useful because, as you've seen up here, these things can get pretty messy if you write them all out. So one way of making this a little bit cleaner would have actually been to define these pipes up here. So we can do something like ePipe is just a little pipeline, and then we can say this is ePipe. And then we can also define maybe like an else pipe, like that. And then define an else pipe maybe like that. So I think that looks a little bit better. You can see everything that's going on. So there's a lot of different ways of writing these things. Just remember that they are useful. I expect that this will be one of the things that you use all the time when you're actually doing machine learning in practice. So one last thing is that if you serialize this model to disk, which is what you will want to do in sort of a production sense, it will retain all of the parameters for every single model. So the standard scalar has parameters, the linear models, both of them, and the random forest all have parameters. All of those parameters will be kept in the same model. And as you might imagine, this is very useful because then when you load it into memory, you don't have to figure out which parameters go with which linear model, what are the parameters of the random forest. It's all just saved in the same model. So again, pipelines and feature unions are very useful. They are really one of the best production tools that we have. And I hope you will start using them as you get to work on your ML mini project. So I really do encourage you to practice these. We will be seeing them again later in the course when we start talking about feature engineering, as they are a really good way to engineer your features. So our our next lecture for today, we're going to start getting into metrics and sort of ways in which we can improve our machine learning. So we've talked a lot about basically how to do scikit-learn, how to use scikit-learn. So now that we're all set with that, we can start really learning about how to build good models using this scikit-learn knowledge that we already have. So thank you.